All right, class, let's get started. Today we are diving into one of the most fascinating and frankly mind-bending ideas in all of physics, the dual nature of radiation and matter. We're about to jump headfirst into a world where the rules of reality, well, they start to get a little weird.
For centuries, the answer to this seemed pretty straightforward. We saw light doing all sorts of wave-like things, creating these beautiful patterns of interference and diffraction. It was solid proof, case closed, right? Well, not quite, because toward the end of the 19th century, a few strange experiments popped up that started to unravel everything we thought we knew for sure.
So our story really begins with a mystery, a phenomenon that had the brightest physicists of the time just scratching their heads. It was called the photoelectric effect, and this wasn't just some small anomaly. It was about to force science to write a whole new rulebook for how the universe works.
Okay, so back in 1887, a scientist named Heinrich Hertz was doing some experiments and noticed something odd. He saw that when he shined ultraviolet light on a piece of metal, it would actually kick electrons right off the surface. These became known as photoelectrons. It seemed like a simple observation at the time, but it turned out to be the first clue in a massive scientific puzzle.
Now, you might be asking, why don't electrons just leave the metal all the time? Well, they're basically held in place by attractive forces inside the metal. So to get out, an electron needs a burst of energy to overcome those forces. We call this minimum amount of energy the work function. You can think of it like an exit fee an electron has to pay to escape. Every metal has its own unique work function.
So how do you give an electron enough energy to pay that fee? Well, there are a few ways. You could just heat up the metal until the electrons literally boil off. That's called thermionic emission. Or you could apply a really strong electric field to rip them out. That's field emission. But it was that third method, using light, that revealed a deep, profound secret about the very nature of light itself.
At the time, the reigning champion of physics was the classical wave theory of light. And look, it was great. It explained reflection, refraction, all that good stuff perfectly. But when physicists tried to apply it to the photoelectric effect, it just completely fell apart. It failed, and it failed spectacularly.
See, according to the old theory, light is a continuous wave, and its energy is all about its brightness, or intensity. So, a brighter light is a more energetic wave. The theory predicted that any color of light, as long as you made it bright enough, should eventually give an electron enough energy to escape. It might take a while for the electron to soak up the energy, but eventually it should happen.
But here was the first major problem. The experiments showed something completely different. Making the light brighter didn't make the electrons fly out any faster. It didn't give them more energy. It just made more of them fly out. The maximum speed of the electrons had nothing to do with how bright the light was. This was a flat-out contradiction of the wave theory.
And the second problem was even weirder. Scientists found that for any given metal, there was a specific minimum frequency, a threshold frequency. If your light was below that frequency, nothing happened. 0 electrons. It didn't matter how incredibly bright you made the light or how long you left it on. Below that frequency, it was a no-go. The wave theory had absolutely no explanation for this.
And here's the final nail in the coffin: timing. The wave theory said an electron would have to slowly absorb energy from the wave over time, kind of like a bucket filling up drop by drop. It could take seconds, minutes, even hours for a dim light. But in the lab, the photoelectric effect was instantaneous. The moment the light hit the metal, electrons were ejected. There was no time lag at all. The wave picture was dead in the water.
So physics was stuck. The classical theory was broken. It was time for a new idea. And in 1905, a young patent clerk you may have heard of, Albert Einstein, stepped up with a revolutionary solution that would change physics forever.
This was during his famous miracle year, where he published a bunch of groundbreaking papers. And in one of them, he basically said, hey, what if we're thinking about light all wrong? He took an idea that Max Planck had come up with a few years earlier and pushed it to its logical and pretty radical conclusion.
Einstein's big idea was this: light doesn't travel as a continuous wave. Instead, it's made up of tiny individual packets of energy. He called them quanta, and we now call them photons. And the energy of each and every photon isn't determined by brightness, but by its frequency, v, multiplied by a fundamental constant of the universe, Planck's constant, h.
And this right here is Einstein's photoelectric equation. It's so simple yet so powerful. It says that the maximum kinetic energy, K max, of an electron that gets knocked out is simply the energy of the photon that hit it, h nu, minus that exit phi, the work function, phi naught. In one clean equation, he solved the whole mystery.
This model explains everything perfectly. It's an all or nothing, one-on-one interaction. One photon hits one electron. If the photon's energy h nu isn't enough to pay the work function phi naught, nothing happens. That explains the threshold frequency. And since it's a direct collision, it's instantaneous, no delay. Any energy left over after paying the work function becomes the electron's kinetic energy, how fast it flies away.
This work was so revolutionary that it's what he was specifically awarded the Nobel Prize for. And here's a great little piece of science history. The American physicist Robert Millikan set out to do a series of super precise experiments specifically to prove Einstein's idea was wrong. But instead, his results ended up confirming Einstein's equation perfectly and even gave us a precise value for Planck's constant. So, what Einstein did was establish a new, strange reality for light. Sometimes it behaves like a wave, but other times, like in the photoelectric effect, it behaves like a stream of particles. This idea of a dual nature opened up a whole new line of thinking.
A few years later, in 1924, a young French physicist named Louis de Broglie was working on his PhD, and he asked a brilliant question. He thought about symmetry in nature and reasoned, well, if light waves can act like particles, could it be that particles, like electrons, can act like waves?
And this is the famous de Broglie relation he came up with. It is just beautiful. It says that any moving particle has a wavelength lambda, and it's equal to Planck's constant h divided by the particle's momentum p. Just look at the symmetry there. A wave property, wavelength, is directly connected to a particle property, momentum.
So, why don't we see a cricket ball wobbling like a wave as it flies past? Well, the answer is all in the math. For something tiny like an electron, its de Broglie wavelength is small, sure, but it's big enough that we can actually measure it in the lab. But for a big object like a cricket ball, its momentum is so huge that its wavelength is ridiculously, unimaginably tiny, way too small for us to ever detect.
Now, this idea of matter waves isn't just some wild theory. It is a fundamental cornerstone of quantum mechanics, the set of rules that governs the entire microscopic world. Experiments have confirmed over and over again that electrons, protons, and other subatomic particles really do behave like waves. They create diffraction and interference patterns just like light does.
Okay, that was a lot of ground to cover. We went from a weird lab result to a whole new understanding of reality. So let's quickly summarize the absolute crucial points you need to take away from this.
All right, here's the breakdown. First, remember the work function. That's the exit phi for an electron. The photoelectric effect is just light knocking those electrons out. Remember why the wave theory failed? It couldn't explain the threshold frequency, why energy didn't depend on brightness, or why it was instantaneous. Then comes Einstein's equation, K max equals h nu minus the work function, which solves it all with the idea of photons. And finally, de Broglie's equation, lambda equals h over p, which tells us that even matter has a secret wave life.
And that's really the big question we're left with. This idea of wave-particle duality just completely breaks our everyday intuition. In our world, a thing is a thing and a wave is a wave. But in the quantum realm, it can be both. It's a profound mystery that physicists are still exploring, and it reminds us that the universe is far, far stranger and more amazing than we can possibly imagine.